Hey everyone, welcome to this explainer. Okay, today we are unpacking some science that, well, it basically asks us to take everything we thought we knew about the physical world and just toss it right out the window. We are literally looking at the potential death of objective reality. I know, heavy stuff. But we're also going to explore how a revolutionary new framework called the Advanced Observer Model is stepping in to help us make sense of it all.
It's kind of the ultimate physics mystery, isn't it? If a tree falls in a forest and no one's around to hear it, does it actually make a sound? Or, to put it in quantum terms, does reality exist in a concrete state if literally nobody is looking at it? Okay, let's dive into this. Because classical physics, it's always told us, yes, absolutely, there's an objective universe out there doing its thing completely independent of us. But quantum mechanics has been quietly whispering a very different story for, the last century or so. And recently, that whisper has turned into an absolute shout.
Just listen to this quote. This is not science fiction, folks. This is a startling, real-world conclusion drawn by researchers Alessandro Fedrizzi and Massimiliano Proietti over at Heriot-Watt University in Edinburgh. After running a highly complex quantum experiment, they concluded that quantum mechanics might indeed be incompatible with the assumption of objective facts. Let that sink in for a second. The idea that you and I can agree on a shared objective fact, like, hey, the sky is blue, or that coin landed on heads, might actually be completely subjective down at the quantum level.
So here's our mental roadmap for making sense of all this quantum weirdness. First, goodbye objective reality. Then, the Wigner's friend paradox. Third, the Advanced Observer Model. Fourth, reality as a streaming video. And finally, securing the quantum future.
Section 1. Goodbye objective reality, the six-photon experiment.
To see exactly how a purely philosophical debate got turned into hard, measurable data, we just have to look at the number 6. That is the precise number of entangled photons used in a state-of-the-art quantum computer at Heriot-Watt University. Now, gathering the statistics using just these 6 photons took the research team weeks of painstakingly detailed work. But those 6 microscopic particles of light, they actually allowed them to test the very fabric of reality itself.
So the researchers used these photons to formally test what's known as Bell's inequality. To put it simply, they set up 2 observers to measure an entangled quantum state. And guess what they found? They proved experimentally that the 2 observers could experience completely alternative facts. Seriously, both observers made flawless measurements, but their realities straight up contradicted each other. Plus, they showed that an observer doesn't even need to be a conscious human. Yeah, it turns out you don't need a brain to establish a reality. Just an inanimate detector as small as a few atoms acts as a perfectly valid observer, totally capable of establishing its own distinct, valid reality.
Let's move to Section 2 and see how this builds. The Wigner's friend paradox, 2 coexisting realities.
And this brilliantly illustrates a famous thought experiment proposed way back in 1961 by the brilliant physicist Eugene Wigner. It actually predicted the exact clash of realities that the Heriot-Watt researchers just proved in the lab decades later. So, imagine Wigner's friend is inside a closed laboratory, tossing a quantum coin. The friend looks at the coin and sees a definite fact. Heads, right? But Eugene Wigner is standing outside the box. He has zero access to the result. According to the strict, weird rules of quantum mechanics, from Wigner's perspective outside the box, his friend and the coin are both entangled in this giant blur of all possible outcomes. The friend inside experiences a concrete fact. Wigner outside experiences a blur of possibilities. 2 totally conflicting realities existing simultaneously. Wild, right?
Now, to really grasp why Wigner sees a blur, we have to talk about superposition. Essentially, a quantum system actually exists in multiple states simultaneously, kind of like a coin spinning in the air, being both heads and tails at the exact same time, until it is finally measured or observed. So, the moment Wigner's friend looks at the coin, boom, they break the superposition for themselves. But because Wigner hasn't looked, the superposition just keeps on going for him. The reality literally depends on the observer.
Which brings us to Section 3. The Advanced Observer Model, rebuilding the universe. So if reality is truly observer-dependent, we obviously need a totally new framework to explain how the universe even functions. Enter the Advanced Observer Model, published in 2024 by researcher Joseph Han-Chong Wong, which attempts to solve this massive paradox once and for all. And it does something pretty incredible. It merges hard physics with deep philosophy. It integrates the sheer weirdness of quantum mechanics with Einstein's theory of relativity. It incorporates the philosopher George Berkeley's idealism, the whole idea that to be is to be perceived, and it draws heavily on the simulation hypothesis, suggesting there's an actual underlying informational structure to the universe.
By combining all of these things, it actively provides a tangible mechanism to solve that exact quantum measurement problem we just talked about with Wigner's friend.
Now, what's really interesting about this model is how it structures the universe into a strict hierarchy of reality across 3 distinct levels. First up, we have R0. This is the foundational quantum realm, and it's operating at the fastest possible speed, the Planck scale. Then we step up to R1. This is the realm of complex systems like atoms and molecules, operating at an enhanced but slightly slower frame rate. And finally, R2 is our macroscopic reality. We're talking biology, stars, everyday objects, operating at the slowest effective frame rate, which is governed by classical mechanics. So basically, the universe scales up by slowing down its information processing.
Moving on to Section 4. Reality as a streaming video, the universe's frame rate.
To truly visualize how these levels of reality work, the advanced observer model takes these super dense mathematical concepts and actually grounds them in a metaphor we interact with literally every single day. Wang describes the universe quite literally like a digital streaming service. The model posits that there is an underlying structure, think of it as a central server, that is continuously transmitting multimedia frames of information to observers. Just like when you're watching a movie on your phone, reality is delivered to you in a sequence of discrete frames. So when a wave function collapses and you observe a definite fact, it's essentially that server delivering a frame of data directly to your specific consciousness or to a detector.
But here is the catch. Your frame rate isn't just random. In this model, an observer's frame rate is tied directly to their energy state and their information processing capacity. The higher your energy state, the higher your frame rate. What this means is that if you have a higher frame rate, you are processing the universe's frames much more rapidly, which gives you a finer, higher resolution experience of time and reality.
And this concept actually makes Einstein's famous theory of relativity incredibly intuitive. Think about a high-velocity observer, someone moving near the speed of light. Relative to someone standing completely still, the moving observer's frame rate is mathematically reduced. Because they are receiving fewer frames of reality per second from the perspective of the stationary person, their clock quite literally appears to tick slower. It's wild. Time and space are essentially just constructs formed from the exact rate at which we process the universe's data frames.
All right, on to our final section, Section 5, Securing the Quantum Future, Cryptography and Beyond.
So you might be asking, why does all this deeply philosophical, mind-bending physics actually matter to you and me? Well, we can take this theoretical concept of observer frame rates and apply it directly to the very real-world problem of digital security. It has absolutely massive implications for quantum key distribution, or QKD, which is exactly how we're going to encrypt data in the future. See, because quantum states alter when they're measured, if a hacker tries to eavesdrop on a quantum transmission, they inevitably disturb it. The advanced observer model shows that by utilizing advanced R1 and R2 observers with sophisticated frame rates, we can drastically optimize these security networks. These advanced observers process information so insanely fast that they can instantly detect the anomalies caused by those eavesdroppers, mitigating information loss and correcting errors in real time.
So the crucial point is how well these secure keys are maintained over time. A standard baseline observer sees some pretty rapid information decay, dropping all the way down to a score of 20. But an advanced R1 observer, like a complex atomic system, slows that decay down significantly, holding steady at 50. And an advanced macroscopic R2 observer, by leveraging its highly sophisticated error correction and frame processing, it maintains a massive secure key rate of 90. Basically, higher frame processing means way tighter security.
We have absolutely covered a lot of ground today, haven't we? From 6 photon experiments in Edinburgh proving alternative facts are mathematically real, all the way to the idea of the universe operating as a giant streaming video server. It completely changes how we view our place in the cosmos. You aren't just passively sitting around in an objective reality, you're an active participant, collapsing wave functions and processing frames of data every single second. So I'll leave you with this to really ponder. What is your frame rate? And how are you actively constructing the universe around you right now? Keep asking questions, keep observing, and I'll catch you in the next explainer.